When you begin to look at linear circuits, and particularly when you look at them without their dynamics, there's some things that you start noticing in terms of patterns. And so if we were to take just a typical structure where I have a box and I have just one, and I have simple constraints. I have just, in this case, say resistors and independent or dependent sources. And I look at this and I take a very particular structure, which I'm going to call a one-port network. And it's a one-port network because you notice I have two terminals. I need to have two terminals, but it's only one port. I only have one connection into this network. Now I can imagine having a 2-port or a 3-port or a 4-port. Typically we don't go much more above 2 ports in our typical analysis, but you can do that. But a simple one-port network, and ask the question, well, is there a way to reduce this, or is there a way sort of fundamentally I would always see in this? And it turns out something is really quite interesting happens. What you find is that any sort of structure that has just resistors and independent dependent sources can, in one level, because it's a linear circuit and it's just going to have a voltage current relationship with some sort of voltage source or some sort of offset in that sort of constant relationship, I can talk about it as having some equivalent resistance as well as having a voltage source in series to kind of model effectively what that offset would look like. And so this gives me one representation. And so what it means is I could take any circuit of that sort and reduce it down to this form, which is kind of interesting. I also can then equivalently, another way to model that is I'm going to have this resistor and a current source, and now they're going to be sitting in parallel. And it turns out I would get the same resistance either way, but I would get a current in parallel or a voltage source in series. And so either of those, and what's nice in one sense is it says I can take any circuit I build, if it's a 2-port kind of equivalent that I want to work with things, I can reduce it to this. This is extremely useful when we get into circuits with dynamics, where I may have a whole bunch of resistors, and I want to just say, what is this equivalent thing? And I can talk about it as a single resistor and then build my dynamics accordingly. So this will be very helpful. It's very helpful for kind of looking at various simplification of these networks. And it turns out that this element with a voltage source has a name because it is really important. We call this a Thevenin one-port equivalent circuit. We also have the one for the current source. It's called a Norton one-port, named after various individuals who looked through these kinds of ideas a long time ago. And so I can look at these structures. But something else very interesting happens here. One of which is I can talk about having a voltage and resistance network. And I could transform it from this port to this port. And all I have to do is then transform the current source based on the voltage and the resistance of that source. It's kind of a nice thing to have. The same thing for going the other way. If I have a current source and a resistor, I could go in the other direction. Again, knowing what the resistance and current is. So this gives me a way to kind of modify things. So sometimes I may have a circuit that looks like I have no interesting way to analyze it. If I shift its representation, I might find I have now this resistor with another resistor in parallel. I can simplify things. I can sort of reorganize my circuit. It gives me an ability with the topology of the circuit I'm building to do some really interesting modifications and changes. And so this is where we're going to find it to be very useful for all of these properties. And so it's really important to just get a really good handle of what's possible in these circuits.